So welcome everyone, and thank you for joining this sixth session. It's on dynamic modeling of climate change policies. So my name is Milot, and I'm the head of the modeling unit at the Department of International Trade for the UK government. So my host is today Zhan Wang from the Center of Global Trade Analysis, and he will be recording as well as to this session, and will help me ensure that we are keep our time. Sorry, I'm just reading. I make some notes. I'm just reading as we go. Okay, before getting to the presentation, I'm going to take a few minutes just to remind everyone of a bit of the protocol and etiquette, so that we make sure that the session is running smoothly today. Apologies, I have chats coming in. Okay, so all attendees except the person currently speaking must remain mute. Unless otherwise noted, the presentation will last 20 minutes, and the session host will verbally prompt the presenter when there are 2 minutes left. But if we do have exceed, then we will be told that we have to shorten the discussion period. So let's try to keep it to 20 minutes based on the presentation. And then after that, we'll have, so the discussion period lasts about 10 minutes. And then so for participants that want to ask a question, either raise your hand after the presentation or just put it on the chat as the presentation goes on. Then at the end of each presentation, we allow about 2 minutes transition just to make sure that the next presenter can load out the presentation and get a bit ready and get in the next session. Then during that transition time, I will introduce the next presenter as well. So today, it's a great session. We have 4 presenters. And without much more delay, I will introduce you to our first speaker. Apologies for the name. So Laerke Jensbye, apologies, from the University of Copenhagen, which will be presenting on nationally determined contributions and scenarios of agricultural emission reduction at country level. So please go ahead. Thank you.
Thank you for allowing me to speak. And you almost had it correct with the name, very close. So I'll take it. It's very good. Hopefully you'll be able to see my screen now. So I'll be presenting some work that I've been doing in cooperating with Francesco Clora and my PhD supervisor, Professor Wusheng Hu. And we've been working on setting up scenarios of agricultural emission reductions at country level using the nationally determined contributions. So just what I'll be going through, brief motivation for this, and then I'll go through our analytical approach in developing these agricultural emission reduction targets. We're using a clustering analysis, and we're doing that because countries have yet to communicate agricultural emission reduction targets. After that, I'll go into our modeling setups and scenarios, and we're using a modified version of the GTAP EID. Last, I'll go into some preliminary findings, conclusion, and then if time allows, I'll dive into future research. So this work here is part of a broader project in analyzing the future of the animal food sector, where my focus is analyzing production impacts resulting from potential mitigation policies, specifically trying to answer the question, what is the impact on future livestock and animal-sourced food production patterns from heterogeneous climate targets? So typically in modeling emission reductions on agriculture, the targets are set in a top-down manner, where the levels are determined that limit the temperature increases to some extent. But in reality, the sectoral targets for agriculture are politically sensitive. So we feel that they must be dealt with individually. And that's even the case for countries with the most ambitious overall targets. So our approach is instead bottom up. We analyze country characteristics and the declared national targets in order to establish sectoral specific targets within agriculture. And that's the methodology that I'll start going through. So we're doing a cluster analysis to elicit the agricultural emission reduction targets. Our coverage is 75 countries, which is equivalent to 90% of the agricultural emissions. And the output from this cluster analysis is a relative ranking of countries' sort of predicted potential ambition for the agricultural reductions. We use this relative ranking in order to quantify a trajectory of emissions based on some assumptions regarding the relationship between the economy-wide target and the agricultural target. So we look at several dimensions, and during this clustering, we look at some economic characteristics, we look at legislation already in place, we look at the growth rates of emission sources, we look at the submission and goal specifics towards the international agreements, and we look at net exports within the agricultural sectors. But actually the first dimension that we looked into was the word use in climate documents. However, we found that these documents are incomparable. The level of detail is more linked to the conditionality of targets than it's linked to actual actions undertaken within these countries. So analyzing all these dimensions, we end up with this relative ranking of country ambitions, where at the top of this table, we have the countries deemed to be most ambitiously tackling agricultural emissions, and then the least ambitious at the bottom, just highlighting a few. At the top, we have like Denmark and Germany and other mainly Northern European countries. Going down a few steps, here we find US, and then even further down, Asian countries such as, for instance, China. So we take this relative ranking and we use that to then generate emission trajectories for each country. And we use that based on a set of assumptions, first being that we can go for the economy-wide target and modify that and obtain the agricultural target. So we assume that these are in some way linked in magnitude. We do several adjustments. First adjustment being this C that is added here. It's a scale parameter using the results of our cluster analysis, where we, for the most ambitious groups, set C equal to 1, and then for the lower ambition levels, we lower the value of the C, which means that we draw down the ambitions related to agriculture. Another adjustment we make is the purple area here. It's a constant that we implement. So in the countries that have already set targets, we observe the gap between their agricultural target and the economy-wide target. And we also include that in our adjustments here. A last element, the blue part here at the end, the G, is a scale parameter that we included so that we're able to scale up or down the global ambitions level, so that we're able to run different simulations, keeping global emissions at different levels so that we can compare to other studies. The resulting trajectory from using this expression on all the countries is the trajectory here highlighted in red. So we have growing emissions. We have just done a linear pathway in the modeling runs here. And we end up in this yellow area, which is what in other studies has been found to be the emissions under a no mitigation scenario, where we just simply apply the economy-wide NDC targets on the agricultural sector as well. We would end up following this black line here, so slightly higher reductions from the emissions. Okay. So instead of looking at it globally, we can also look at the trajectories for individual countries. So at the top parts here are countries that we're expecting to reduce emissions. So US, Denmark, Germany. And if we think back to the tables, Denmark and Germany were some of the countries we deem to be most ambitious. You can see that they're reducing their emissions at a faster rate than, for instance, the US here. Just a note, the y-axis aren't similar, so you cannot compare across. This is just to show the trajectory. At the bottom here, we have some countries that we expect to have increasing emissions from the agricultural sector. So that was the emission trajectories. Another input into our simulations is emission intensity updates for the agricultural products. So here we have 3 sets of scenarios that we implement. So we have one we call the historical trend, which is just the calculation of the yearly growth rates using the historical data. But we have a scenario we call the accelerated advancement, where we simply double the historical trend. And then we have a third scenario where we model a catch-up development, where the laggards, so the countries with the highest emission intensities, are reducing their emission intensities at a higher speed than the front runners, so they're catching up. A better way to maybe understand this is to look at an example of these different scenarios. So we have the annual changes in emission intensity here for raw milk. On the graphs, we have the logarithm of the emission intensity in 2017. And on the y-axis, we have the yearly growth rates. On the left-hand side, it's the historical growth simulation, which is what we use in our baseline development. And here we can observe that the countries with the lowest emission intensities also seem to be the countries reducing at the faster speed. However, if we do not take the trend across all the countries, but just the front runners, we see the reversed relationship, that the countries right at the frontier are reducing at a slower speed than the countries catching up to them. And that pattern is what we have extended when we look at our catch-up development scenario. So here we, for all the countries, have implemented that the countries with higher emission intensities are reducing at a faster rate. So now we finished with the input, and we can go into dive into the modeling. So we'll be talking about the setup and the scenarios. So we're using a modified recursive dynamic GTAP model. It's an extension of the GTAP ERD, but it includes non-CO2 the non-CO2 emissions database, as the focus is on agriculture. This is quite important. And following some work of my collaborators, this model allows for multiple country and region emission trading systems. So it allows for us to implement different emission targets for the agricultural sector and for the non-agricultural sector. And lastly, we also included some emission intensity shifters within the model. So the baseline setup in our run here follows an SSP2 set up for the macroeconomic development, so the GDP, the population, the labor force growth, as well as some adjustments in some efficiency and technological improvement parameters. And the scenarios that I'll be presenting here in the results are listed here in the table. So it's the blue row here and the yellow row. They're built upon a baseline where we shock the non-agricultural sectors, so that we, after the policy run, meet the economy-wide targets submitted under the Paris Agreement. And in the baseline, we then, for the emission intensity development, have the historical trend. So the way that the policy runs different is in the assumption of the emission intensity, where we in the second here assume the accelerated advancements, so the double speed. So some preliminary findings. If we look at, start out looking at the agricultural production value, this is relative to the baseline in 2030. And we see that for most countries, the agricultural production value is increasing as a result of the emission reduction target being implemented, though not for the countries with the strictest target, here being Denmark and a couple of other European countries. But for the other countries, the production value is increasing during this run, and that's given some competitiveness shifts that are moving production towards these other regions, as well as some increased price levels as a result of the lowered supply. If we zoom out for a second, instead of looking specifically at the agricultural sector, look at the economy-wide GDP impacts, we see that for some of these countries, the higher targets, it actually has limited economic impacts. For instance, Denmark here, that had a high production value reduction, the impacts on GDP is barely noticeable, whereas the impacts on some of these developing countries where the agricultural sector is more important to the economy is much larger. Just a note here on the Asian side of things, where the GDP seems to be growing. So specifically for East Asia here, it's because the way that the emission restrictions are implemented, it is not so stringent in East Asia. So a lot of the production is moving towards this region in our policy run. If we also look at the emission taxes here, just to confirm that the model is acting as we would want it to, we observe that the countries with the more restricting targets, that they also have higher tax rates. But also we observe that countries that we have an expected peak of emissions in the future, so countries like China, India, or regions such as sub-Saharan Africa, actually also have to restrict the growth of their emissions by implementing positive carbon taxes in order to follow the trajectory that we've modeled in this case. Last note to this figure here is the comparison between the two policy runs that I'm shown here. So we can observe that this faster emission intensity reduction results in lower carbon prices. If you look at the China case, it almost seems to be proportional. So twice the speed of emission intensity development, half the emissions tax, but that's not the case for the other regions and countries. So last slide with some data here is with the production shifts within the livestock sector. Here looking only at the impacts in the first scenario, so the one following the historical emission intensity trend. At the top figure here, looking at the production quantity changes relative to the baseline. So what is observed here is that there is the largest impacts on the ruminant meats for most countries. This is also the product among these three with the highest emission intensities, so it follows a pattern one would expect, but there's countries well, there are some exceptions in some of the countries. So for instance, China, Ireland, sub-Saharan Africa, it's actually the milk and dairy production with the highest reductions relative to the baseline. If we look at the changes in production quantities relative to the start of the policy, we observe that for most countries, there's actually an increased production level across these three goods. And that's linked both to the population and economic growth modeled in the baseline, but also driven by the emission intensity reductions, allowing for larger productions without having increased emissions. So that was a few of the highlights in the preliminary results. Just briefly go through a conclusion and some future research avenues. So what I've presented here today, first the cluster analysis, which we believe provides some guidance on how to develop these agricultural emission reduction scenarios, because we try to model what one would expect that countries are assumed to apply divergent reduction targets in relation to their circumstances, as well as their overall ambition levels. When we look at the results and summarize what we presented here, what we observe is that when we look at the effects on the production patterns, the emission intensity products, so in this case ruminants, are affected more. If we look at the divergent agricultural ambitions and look at the impacts on the macro scale, we found that given that most developed countries have a small share of GDP being from agriculture, the implications of setting restrictions have limited economic consequences. And the reverse being the case for the developing countries in our modeling run here. Additionally to that, we also observed that for the countries that have expected to have peaks in their emission intensity, in their emissions in the future, such as China, the actual emissions would be even higher in our modeling run had we not had a positive carbon tax. Last bullet point here, the emission intensity reductions, the way that we modeled them here, implies a lower cost of reducing emissions when they're increased. Some future research avenues, be looking into having a better specification of land. So currently we're just following the standard land endowment, but we would look into including the AESET database to have a better modeling of this. Additionally to that, we'll be looking into having a better link between investment and the emission intensity updates. So having some abatement cost structure, because currently it's just an exogenous shock. So it's sort of a free advancement in the technology. And the third point being looking into extending our baseline and scenarios towards 2050, but there we run into issues of lack of targets, or at least some unclear, not clear goals when it comes to the neutrality targets, because we do not know at this point how much of that is going to come from carbon capture storage or actual reductions from emissions within the sector. Yeah, that was the last slide, last point. Yeah, so give the word back to the chair of the session.
Thank you so much for a great presentation. And spot on time as well. So is there any questions or comments or suggestion? Please raise your hand or put them in the chat.
I raised my hand.
Yes, go ahead, please.
Thank you. I'm going to just, okay. Thank you very much. Very nice presentation. I have a methodological question, and maybe I apologize because maybe I missed something that you already said at the beginning of the presentation. I was wondering about what you call emission intensity. Maybe you have defined it at the beginning, so I'm sorry, but it's emission intensity of what exactly, of GDP or what you consider as emission and intensity? And the second point is just you impose this as an exogenous constraint, and then a carbon price is calculated endogenously in order to respect this constraint.
So the second question, yes, that is the way that it's modeled. Yes, to the second question. So the first question. So in the way of calculating the growth rates, there we're using the FAO definition of emission intensity. So that's relative to a production level.
Okay, great.
So that's in quantities. Yeah. So that's
okay. Yeah. Thank you.
Thank you. Any more questions, comments?
I think there's a hand from Julia.
Oh, apologies. I do not see. Probably I have to.
Should I stop sharing so that you're able to see people?
Yes, thank you.
I'll just do that. Okay.
Yes, now I see. Thank you. Yes, Julio.
Okay, can you hear me?
Yes.
All right. Thanks for your presentation. Very nice and interesting research. I have two questions. So the first one is just maybe it's myself, but can you briefly explain what cluster analysis is actually, and how are you using your variables? You said that you're using several variables like GDP and other variables to create this ambition ranking. So how do you, what is actually cluster analysis? I'm a bit confused there. And the second question I have is, can we have or expect carbon leakage to happen in this setup in your model? Because if I understand correctly, your tax rates are calculated implicitly and the emission targets are met, then probably you cannot have carbon leakage. Or do you have carbon leakage in your model? Thanks.
So I'll do the same. I'll answer the second question first. So right now we're okay. Some noise. In the modeling right now, we're forcing the emissions. So we're modeling that exogenously. So calculating carbon leakages doesn't really make sense in the current implementation. Or we could then take the tax rate from our modeling run and do some simulations with them, because then we're not forcing the emissions, I suppose. Cluster analysis, yeah, it's not really a CGE thing, so I understand the confusion. Essentially, it's just looking at different variables and grouping countries together that are similar. So for instance, one of the dimensions that we look into is economic characteristics. So there we look into GDP per capita, but also food security and the emissions share coming in from agriculture. So there we group countries that are similar. So there's a group of countries with that have high economic levels, low food security issues, high emissions coming from the agricultural sector. And if they have these three things, we would expect them to do more than a country that is low in income, has food security issues, has no emissions coming from the agricultural sector. So we look at the clustering analysis as a way to distinguish between different sets of countries, and then after having these sets of country groupings, we rank them. Does that partly make sense?
Yeah, thank you. So just a follow-up question. So, and do you also use for this cluster analysis the national intended contribution? So for each country, you already have a number of how much they want to save in emissions. Do you use this number as well?
So we use that subsequently when we calculate the trajectories. But no, we use sort of the goal specifics. So that is like, are they including all the greenhouse gases in their targets? Are they including all the sectors in their targets? Because if a country don't include the agricultural sector as a sector to reduce emissions, we don't expect them to do something related to agricultural emissions. So that's in the dimension I presented with the submission and goal specifics. There we also keep the track record of whether they're submitting their documents under the Paris agreements. So are they submitting the NDCs? Are they submitting all these other documents? So no, we don't include the actual level of their reduction, but that's what we use subsequently when we calculate our trajectories, because that's where we start out with our economy-wide targets, to have that dimension as well.
Thank you.
Thank you. Yes, Angelo.
Hi. Well, it was a very nice presentation and very nice work. I think there's not many studies out there that try to compare this bottom-up approach of future emissions in agriculture and mitigation. Something that got my attention was your trajectory of emissions in the historical period and then for the future, and the future is an assumption, right? Mm-hmm. And for some countries like China and Brazil, there was a kind of a steep increase on those emissions in the future, although the historical trajectory doesn't have the same upward inclination. And my question is about that. Why are you guys expecting that sharp increase on those emissions for those countries if the historical increase was not that high? And if this trajectory, you make much difference in your simulations, since when you impose the target, those countries will need to do more than other countries, or you would expect that they would have less emissions if you impose the same target and that the future projection was not that steep?
Yes. Okay, so for some of these countries, it's related to population growth, of course, drawing up the emissions from agriculture, but also related to the expansion of livestock sectors as well. You're right that we have that for some of them it goes above or well above the historical trend, and that seems quite extreme. But it also relates to the that what we're implementing here is their targets for the agricultural sector, so whether they've set targets. And some of these countries, the way that they have set their economy-wide goals is as business as usual scenarios. And some of these business as usual scenarios, the way that they're simulated, draws up the economy-wide emissions very high. So when we do it relative to that, it becomes sometimes some extremes. But it's something that we'll look more into and run some different simulations where maybe for some of these extreme cases we'll force them to follow the historical trend instead, because you have good eyes, and that's an important thing. Yes.
Yeah, thank you. Well, I'm particularly interested in Brazil, since the target from Brazil is not a business as usual related to a business as usual emissions, the target of 2005 emissions. And another curious thing is that the livestock headcount is stabilizing the country, and there's a specific policy targeting agriculture there. So it was my question was, when we look at those specificities for that country, we see things that are hard to sustain that sharp increase.
Okay. Well, I don't know much about Brazil, to be honest, not specifically, but I'll look into it.
Yeah,
so,
just a suggestion, since you are dealing with all the countries, so it's quite hard to get what's going on in each one.
Yeah. Thanks for the comment.
I suggest that we follow up with Angelo afterwards. I think obviously he has a lot of knowledge there.
Yeah, I'll send you a message if you have a lot of knowledge.
Thank you. I just quickly, we have one last question, if you don't mind, and then we'll move on to the next presentation. David, please.
Yeah, thanks for the presentation. Hopefully just a quick one. There's two questions. So I put it in the chat, but I'm not sure if it is showing up. So firstly, I saw some of the countries had like negative carbon taxes. And I guess, how do you, like, what do those represent in your like explanation of the results? And then just on the data side, I was wondering, is there like an accessible database on the NDC and intensity targets, or did you basically create this for the purpose of this work? Or like, what was the source for those? Thanks.
Yes. So the reason why some of the carbon taxes becomes negative, so it becomes a subsidy to some extent, is because of the how the emissions are forced in the model. So that's in order to have that growth rate in the emissions in the modeling run, it forces a negative carbon tax. That's what happens in order to meet the trajectory that we've exogenously imposed. I think it mainly happens for a couple of Asian countries. Your second question related to, what was it, the NDC targets? Whether there is a database of the targets?
Yeah, basically on like the data side. So like, is there like a data set that you got these from, or did you actually go through the agreement, or like what was the source? And then also the intensity changes as well.
So the intensity changes is there I'm using the FAO data. When it comes to the NDCs, I've been looking through a bunch of different data sets. So there is a data set by IGES that has sort of the overall targets and stuff. But then I've also been looking at Climate Watch data. I've been looking into specific countries' submissions, because all these databases aren't updated when it comes to countries that have recently resubmitted. So there I've been looking into the documents. Yeah. So hopefully that answered.
Thank you.
Perfect. Thank you so much for a great first presentation and discussion. So we move on to our next presenter, which is Juha Honkatukia from the National Institute for Health and Welfare. We will be presenting on climate policy and green transition, a CG analysis of the Finnish 2035 carbon neutrality target. The floor is yours if you're ready. Thank you.
Yes, thank you, Madam Chair. Let's see now. I'm going to need a pointer, so I'm trying to get it working. Yes, here we go. Yeah, so this is a study that sort of contributes directly to the political debate and decision making. It's sort of use of a CG model to sum up strategies that are implemented in various sectors of the economy. There is some economic optimization going on, but I think mainly the model here is actually used to sort of get an idea of the welfare effects and the macroeconomic effects of the policies that are being planned. So a lot of weak links to modeling that's done with sector-specific models in the agricultural sector, in the energy sector, in the transport sector, and then also in some industrial sectors. So I'll try and give you an idea of what's going on. When we're trying to present these results to the decision makers, it's usually quite aggregate things, macroeconomic things that they're interested on. So I'm taking it as a habit to sort of explain that if something's happening in the economy, then there has to be something going on in the supply side of the economy. We'll have to sort of see some movement in the use of resources in the formation of value added between sectors, maybe changes in how much labor is going to be available, and if there's any transitionary unemployment, that sort of thing. But I think when we're talking about this transition, it's essentially about huge investments which are causing productivity changes, productivity growth in different sectors of the economy, and also they're going to be affecting the sort of material efficiency, which is a form of technological change in the economy. So the prior, I guess, is to expect that we would have to see a lot of productivity growth compared to the baseline, because we are putting in a lot of money in these new, better, more efficient technologies than were used previously. Something has to happen in the demand side, and I think this is where the economical bits have an effect. So if you are to sort of impose or enhance changing the structure of the economy, then economic measures usually hit the user of fossil fuels or energy and so forth. So they create the incentive for investment in these new technologies. At the same time, because the investments are quite big, they also have an effect on directly sort of causing a boom, if you will, in the construction sector, and if only for the fact that something like half or even more of any investment is actually construction. Right. So the model that we are using in this is based on the Victoria University or Monash models, which I think are quite well known for most of the people. So I'm not going to be going much into the details of that. But essentially, what it's about is that it's a rather large scale, something like 150 commodities and 100 industries, recursively dynamic model for Finland. There are some extensions which have to do with the welfare bits of the model, which I'll say something about briefly at the end of this thing. So we have a WEM scenario with existing measures. This is European Union jargon. That's the baseline for everybody else, but it's WEM for us in the Union. One of the challenges for this thing was that we had to start from something like 2019. And that means that we have to sort of have an idea of how the economy is going to be sort of recovering from COVID. Well, I think what we've learned from COVID is that the economy in many industrialized countries is surprisingly resilient. So during all of it, we never saw a drop in household income at the aggregate level in Finland, for example, though that's perhaps partly caused because of the welfare system of the sort of Nordic model, if you will. But nevertheless, I think it's remarkable, and then that means that now that most of the restrictions went to sort of fighting COVID are removed, we were on the way to a nice recovery until something else happened, but I won't go into that. So this was completed at some time in January, I guess. So we didn't know that there were more surprises coming. Anyway, COVID is something that's sort of vanishing. But in the Finnish case, this decomposition of the growth on the supply side shows that there's a sort of recovery in the labor input, but after that there's not much contribution from labor input at all, and that's a reflection of the age structure of the population. We are actually in a situation where the contribution of where the number of people in working age is actually shrinking, and it's going to be shrinking well into the 2040s, actually more than that, well into the 2050s. So everything already in the baseline is actually hanging on productivity growth and investment. Well, this was the bit about the recovery that we were sort of seeing an export-driven growth. Maybe I should say something about the structure of exports in the Finnish economy. We produce investment goods. Our neighbor to the west from us, Sweden, produces much more consumer goods, and their exports were much harder hit than the Finnish exports for some reason. But that's maybe why the exports, they did drop initially in Finland as well, but they have started recovering already last year. So that was the situation that's in the base. Well, one of the inputs that's playing a very large role when we go from the baseline WEM scenario to the WAM scenario, which means with additional measures, we can just call it policy. So in the policy, what's going to happen is that Finland is trying to achieve a carbon neutrality target by 2035. And that means a huge investment in getting rid of fossil fuel in the power sector. Turns out we didn't have very much of that left. There was some coal, for example, the CHP production. There was some natural gas, also for CHP production. But then renewable energy like hydro and then wind, they were already there. And hydro is something that you can't really increase anymore. I mean, the suitable suits or locations, they have already been sort of harnessed. But wind is obviously on the rise, and in the policy scenario, that's going to increase quite a bit. Finland has quite a bit of nuclear as well, you might notice from here. We have 4 plants at the moment. The 5th is just coming online, and then they account for something like 40–50% of all the electricity production. So while it's not renewable, it's at least at the plant side, it's not producing emission. One thing about the policy and electricity that's worth mentioning is that if you think about the structure of the policies, at the European level, emission trading is covering most of industry and most of energy production as well. So there's not very much leeway for national policies in those sectors. Where something does happen which is sort of under the mandate of national policies is transport sector, and then to an extent that's things like the housing sector. Well, transport sector it's not the biggest producer of fossil fuels, but it's probably emissions, but it's probably one which is a lot more difficult to tackle than, for example, industrial emissions. In the industrial sector, some of the policies that we have in this, as they call them, roadmaps, what the sectors can think that they can do if they invest enough is, for example, that they can get rid of coal in the production of steel and replace it by hydrogen, which requires a lot of electricity, but if the electricity is available, then you can do it. And the magnitude of these changes is something like, in the case of Finland, there's one factory in particular that is planning to do this. Is something like 4 million tons of CO2 in a year, out of national emissions, which are less than 50 million tons a year at the moment. So these contributions are huge. If you want to do the same sort of a thing in the transport sector, it's much more difficult because you're talking about privately owned passenger cars, and then of course lorries and stuff like that you need to do, to keep the industries rolling. But the technology doesn't allow easily for the replacement of the whole fleet of passenger cars, like they in a way do in these huge mills. So there's going to be a transition period to get rid of fossil fuel in the transport sector. But what's going to happen is that it's going to be fossil fuels are going to be replaced by electricity, and that has a bearing with this picture because it seems that many people think that this is going to cause a huge peak in electricity demand. Turns out it's not going to do that because electrical vehicles are so much more energy efficient than the fossil fuels driven cars that they're replacing. They are happy to provide the same passenger service, if you will, with something like a third of the energy. So there's a bit of an effect on electricity production, but it's not massive. And here's the transport sector, where you can see how the sort of powering energy sources, if you will, of the passenger car fleet are going to be changing actually quite rapidly. The whole fleet of passenger cars is something like 2.3 million, I think, at the moment in Finland. And a third of that is supposed to be all electric by 2030. So that's a very rapid change. I think at the moment we have less than 100,000 vehicles which are fully electric. So a huge increase. But that's something that is entailed in the policy, and by the pricing that the European car makers are sort of following at the moment, it might be feasible if they just get the cost produced with this with this raw material gluts that they're facing at the moment. But that's assumed in the policy. The macroeconomic bit of this is, I think, in a way quite interesting. If you look at the supply side of the policy compared to the baseline, what happens is that there's quite a bit of boom, depending on whether we are in the phase of big building of these new technologies, whether there's a lot of investment going on. And then we are essentially making many of the sectors of the economy more capital intensive, if you will, than previously. But because all of this investment is going on, it has the effect that during this investment booms, the price of investment for all of the economy is going to be higher. And that means that there are some sectors which are not going to be investing quite as much as they were in the baseline, because these changing sectors are getting rid of fossil fuels by investing massively. But in the end, what's going on is there's quite a bit of productivity growth, which is showing up as the contribution of technology. That's not only labor productivity, it's also material efficiency and things like that. Then there's another thing that's going on, and that's actually the only thing that's really causing a negative impact on the GDP. The contribution of indirect taxes is to the GDP growth is negative. Well, it should be, because we're getting rid of the tax base for fossil fuels. So it's loss of the tax base which is actually causing most of the negative impact on a bit longer run. And the productivity growth that you're getting from this transition is what's going on the good stuff. We have employment and things like that, but I'd like to concentrate on these regional effects. This is something that the politicians are interested, because they come from a particular region, so they have to know what's going on, and they have to justify what the government is doing to the respective voters in the regions. The big picture is that the sectors where services and these key industries which are going through the transition have a large value added, so they have a smaller share than the ones which don't have these industries. So if you only have sort of losing industries, then it's going to be a little bit more difficult for you. But again, if you look at the deviation from baseline in a 30 years time, even 1.8% or 1.5% compared to the baseline in terms of economic growth, it's not really very much, because the average economic growth during that baseline period is hovering around 1.5% a year. So even the worst hit regions of the country are losing something like 1 year's worth of growth divided over a period of 30 years. An interesting bit which we also found, we have combined data from household surveys and then data that sums up. I think it's called the transfer account that sort of tell how household get transfers income transfers from various other sectors of the economy, how they pay taxes, and where they get their income. So we have direct effects from these energy prices on household income, and then we also have the income effects that stem from changes happening in the economy. And what's striking here is that at least it used to be, at least in Finland it used to be, when we were talking about things like raising energy taxes, somebody would be objecting that this is actually going to have a regressive effects on income distribution. But it turns out that rich households have 2 cars, maybe they have a cottage, they travel a lot, and so forth. So they're in proportion to their consumption, energy might not be as large as it is for some of the lower income deciles. But indirectly, they are using quite a bit more energy, both in absolute terms and also in relative terms. And then it seems that if you implement all these policies, then the richer, more polluting households are going to be hit harder, both absolutely and relatively. And that, I think, is encouraging because to me, that seems just. Yes, and I think that was pretty much my last slide. So when we go to this welfare bit, it's not the case that they are nil. There is a cost to all of this, but it's not very big if you think about the time span. If we're just talking about years growth, as I was saying, tops. So divided over 30 years, that's 0.1, 0.2% per year from now on, which is not much by any measure. And then this thing that actually, if these policies are sort of uniformly and systematically implemented, then the end result in terms of welfare will also be something that's just meaning that people are more likely to actually vote for it, which is necessary to get it implemented. Yes, thank you, Madam Chair. I think I spoke a little bit too long, but not by much.
Oops, I'm back. Thank you very much. Great presentation. So I'm going to turn to the participant to see if there's any questions. And we already have. Hi, Dominic. And yeah, great. Dominic, please go ahead.
Thank you, Katrine. Thank you, Juha. That was great. I came in a little bit late, unfortunately, because I was somewhere else. But I was a bit surprised at the transportation chart, because not only do you have decarbonization, but you also have a huge decline in energy. And yeah. I'm trying to understand what was driving that, because for me, transportation is pretty income elastic. Yeah. So I would expect the demand for transportation services to climb pretty sustainably over the period. But you have this huge decline in the energy necessary to meet the demand for transportation services.
Yeah, so yes, a good observation. Nice to see you, Dominic, and thanks for the question. So what's driving it is this thing that the transport sector is going all electric. And an electric vehicle is running or providing the same passenger services using something like 1/3 or even less of the energy of a fossil fuel driven passenger car. It's a bit more difficult in the cargo sector because you can't really think of going all electric in that sector, but then you have solutions like biofuels, which might help a little bit in that sector. Buses, local transport, that is something that can go electric. So it's but I mean that's the big picture there, and the big scenario that's going on. We're getting rid of fossil fuels all aboard and then replacing it with electricity. I think some engineers would claim that in 30 years' time, there is going to be another alternative, and that's hydrogen. But with hydrogen, you have the same sort of, advantages compared to most fossil fuels. So that's my answer. I mean, that's why it can happen. In terms of passenger kilometers and so forth, there's only a slight reduction. And then I guess, yes, well, you're used to what's going in an economy where the population is growing, the Finnish population is not growing. So there's not this sort of an inherent upward trending in the demand for transports. Hope you're happy with it.
Thank you. Yes, Larry.
Hello, everyone. Thanks for the great, interesting presentation. And as you pointed out, and also it is widely agreed, technology or productive growth play an important role in our projects emissions in the baseline, and also play an important role in the emission reduction. So, but it's often very difficult to project technology progress, technology growth. For example, 10 years ago, it was hard to predict that, to foresee that the price of wind and solar generations not decrease a lot after just 1 decade. So I wonder, can you explain a little bit more how you calibrate your technology progress in your baseline, and also is the technology change is endogenous or exogenous in your scenario?
It's only, excuse me, it's only endogenous to the extent that there's a sort of sectoral change in the economy. The bit that had to do with, for example, the transport sector, take use of transport sector modeling, which sort of give an idea of how the passenger car fleet is gradually moving into vehicles which are running not with fossil fuels, but with electricity. Something similar goes on in the power production sector, but as I said, the transition in the power electricity sector, it's kind of already halfway through. So there are going to be some big changes, but it's less dramatic than in some of the industries. The industries, well, we are doing this together with energy and process engineers, and their sort of mantra is that all the technologies that we are going to be using during the 30 years from hence, they are already there. So it's just a question of when the prices are going to be low enough for them to be taken, online. So there is an idea that, for example, with biofuels, the first refineries are going to be more expensive than the next ones, and there's some investment in biofuels already in the baseline, and in the policy scenario. Then it depends a little bit on what's happening with the price of electricity and other sources of energy. So the technology model, which is something actually most of you probably have heard about, the times model that's used by the IEA. So the times model is predicting when these investments are going to be taking place, and the economy model is taking that as a given. But I am doubting the energy engineers a little bit, so I've done it two ways. I mean, if you believe that these guys are going to invest, let's say, in the biofuel refinery, and I think these guys who are making the decisions have been asked if they are considering this. Then there are two things that one of two things that need to be happening. Either they have to accept that there's they have to have an idea that the expected profits from this investment make it viable. So you can use the expected profits to calibrate the model to repeat that investment. Or you can think that the expected profits are not going to be enough, but if you still want to have that thing online, then the government has to give an investment subsidy. and then you can report that this is great technology and it's going to be helpful in reducing the emissions, but it involves a cost that the government must face, and ultimately the consumers or the taxpayers have to sort of foot the bill.
Thank you. If I'm allowed, can I ask another question? Because when you decompose this GDP, you decompose on the supply side, you decompose the GDP contribution between technology, capital, labor, and just the indirect taxes. I don't understand why
the taxes?
This indirect taxes, but conventionally in this macroeconomic, this growth accounting, people usually decompose GDP between just technology, capital, labor, because they are the contributors. That
is two people do that, but that's actually the composition of value added. If you want to decompose to GDP, you have to include the indirect taxes. If you don't, then the supply side and the demand side both match. So it's a question. I mean, I have to sort of repeat many times, but that's just the definition of GDP. So GDP is value added plus.
But taxes do not contribute to GDP at all, right?
Well, according to the definition, they actually do. So it's a technical point, but they are included. I like to report them because if you didn't, you wouldn't get the insight that the GDP loss is actually only due to the loss of the tax revenue. So it's yeah.
Okay, thank you.
Thank you very much. Do we have one last question or comment? If not, then we'll move on to the next presenter.
Thank you very much.
Thank you. A very good presentation and good discussion. Thank you very much. Yes, so next presenter is Meriem Hamdi-Cherif from the OFCE Sciences Po French Economic Observatory. We will be presenting on assessing short-term and long-term economic and environmental effects of decarbonization pathways in Tunisia. When you're ready, please go ahead. Thank you.
Meriem, you're muted.
Yeah, you're muted.
And now it's okay.
Yes, perfect. Thank you.
Sorry. So I was saying thank you very much, Catherine. And yes, indeed, I'm going to present this paper entitled Assessing Short-Term and Long-Term Economic and Environmental Effects of a Deep Decarbonization Pathway in Tunisia. And this is a work that has been done in collaboration with my two colleagues, Frédéric Reynès and Gisela Londa. And I'll come back to this point, but this study has been financed by the United Nations Development Program. Oh, why it doesn't work? Sorry. Sorry. So yeah, before just to put things into context, let me remind that the Paris Agreement called on the parties to the UNFCCC to undertake an ambitious climate policy to achieve carbon neutrality by 2050. And in view of the urgency of climate action, the governments of the various countries must undertake structural reforms and put in place the conditions to promote socioeconomic development that is low in greenhouse gas emission and resilient to climate change. So in this context, the elaboration of a deep decarbonization pathway strategy can represent for developing countries and for Tunisia in particular an opportunity. It can be seen as an opportunity in order to revitalize economic growth while reducing GHG emissions at the same time. And talking about GHG emissions for a country like Tunisia, this make the focus on energy. And just a few points about the Tunisian energy context. Let me highlight the fact that Tunisia actually suffers from energy deficit, and it's highly dependent on fossil fuel imports. The burden, there is the issue of fossil fuel subsidies that is very important, because, for example, the burden of fossil fuel subsidies on public finance is very heavy. It represents approximately almost 3% of the GDP in 2021. We have the issue of high energy bills for the poorest households, etc., etc. So the idea of this paper is actually to investigate the macroeconomic effects of the implementation of different measures that I'm going to describe in order to achieve significant climate mitigation objective. The simulation conducted here investigate the implementation, as I said, of different measures. The first one is a significant we investigate the significant penetration of renewable energies in the electricity mix. More precisely, we consider a target of achieving 80% of renewables in the electricity mix at the end of the period in 2050. We also consider the total removal of fossil fuel subsidies very soon, in 2025, and the introduction of a carbon tax in the Tunisian economy. This is much more a technical point, but we also have implemented the introduction of price signals in order to achieve the energy consumption that is foreseen in the low carbon, national low carbon Tunisian strategy. And in the exercise we have implemented, all these measures has been implemented incrementally, and I'll come back to this. An important point here, there are two scenarios that I'm not going to describe in terms of results here in this presentation for the lack of time, but the thing is that concerning the scenarios with price instruments, namely energy subsidies removal and carbon tax, we have considered two kinds of scenario. First kind of scenario, without recycling the revenues generated by the implementation of these policies, and another two other scenarios where we consider the recycling of the revenues generated. And as it is quite well known in the literature, the recycling of the revenues generated actually stimulate economic activities, counterfact the recessionary effect of rising energy prices. So here in this presentation, we will show the results concerning only the scenarios where we recycle the revenues generated by these two policy instruments. So the way we have recycled these revenues, we have considered two specific rules. Concerning the carbon tax revenues, we have used them to feed the Green Transition Fund over the period considered, that is 2021 to 2050. So there is a reverse. The revenues are reversed to households and businesses according to the priorities defined by the Green Transition Fund. So it is very green oriented. While the energy subsidies revenues, they are that has been removed. They are recycled according a lump sum rule. Households get back the equivalent of the amount that has been removed from them in a lump sum form, and the productive sectors share the remaining amount in proportion to the weight of employment of each sector in the total employment. Actually, to do and to implement all these scenarios, we have used the 3Me model. The 3Me model in its Tunisian version, and this paper is the fruit of this 2-year program that has been financed by UNDP in order to develop multi-sector general equilibrium model for Tunisia in order to study the green transition. So what is 3Me very briefly? It is a country level, multi-sector, it's hybrid, it's dynamic, it's an open source, and it's a CGE model. It relies on hybrid matrices in money values and physical quantities concerning energy in order to ensure consistency between the engineering-based and economy-based analysis. And actually, 3Me describes dynamic trajectories in 1-year step through a recursive succession of annual static equilibria. And actually, this model represent, let's say, the second best nature of economic interactions. Among the second best feature, we can say that we have this very important feature here, that prices don't adjust instantaneously to clear markets. Actually, prices and quantities adjust quite slowly, and producers adjust their supply to the demand. And this this has the advantage to allow for situations of market disequilibria in pockets. In particular, we have the possibility of having involuntary unemployment through Phillips curves. And another last important feature is that agents have adopted imperfect expectation for their investment decisions. Okay, just to sum up of the scenarios that has been implemented in order to study the national low carbon Tunisian strategy. We have considered a first scenario that is called REN scenario, where we have implemented a single policy, that is the significant increase of the share of renewable energy in the electricity mix. A second scenario where we complement this let's say standard measure with the removal of fossil fuel subsidies, and then a last scenario, complete scenario of that correspond to the low carbon strategy of Tunisia, where in addition to the share of renewables, the removal of fossil fuel subsidies, we consider the carbon tax and price signals with, as I said, the recycling of the revenues. So concerning just the level of the carbon tax, before 2030, we have the level of this carbon tax that is calculated in order to cover 100% of the Green Transition Fund. So it represents, since the level of emission is quite high, and at that period, the need of the GTAP is quite low, the level of the carbon tax at the beginning of the period is quite low. It started from 1.1 dinar to 9 dinar in 2030, and then after 2030 the carbon tax trajectory is defined to meet the 2050 emission reduction target, and we arrive at a level of almost 400 dinar in 2050. So let's move on to the results now, and just a small remark. As we do in these exercises, all simulations here are presented, or the results of the simulation, sorry, are presented in terms of deviation to the baseline scenario. In most of the case, in relative deviations, and in case of employment, it will be absolute variations. So if we look first at the environmental effects and we look at CO2 emissions, we observe, whatever the scenario, a continuous reduction of emission over the period. So we have a decrease of 36% at the end of the period in 2050 compared to the reference scenario in the renewable case here. And when only one policy is implemented, then if we add to these the subsidies, the removal of the subsidies, it increased a little bit, reaching a 42% reduction. And if we implement all the package with the carbon tax and the price signals, we reach significant reduction, almost 70% at the end of the period. So if we look now at some macroeconomic indicators, we start by investigating employment. Here I show the results in an aggregated way, but 3Me allows for looking at the results to look at the sectoral results, sorry. But here they are presented very aggregated. So what we look in terms of employment is that actually, although the effect in the different scenario don't sum up exactly, properly speaking, we actually observe a virtual accumulation of the positive effect which prevail. In the renewable scenario, there is a continued growth in additional jobs, because here, we have this is not in relative, this is a variation with respect to the baseline, but it's an absolute variation. Here we have thousands of additional jobs compared to the baseline. So the increase affects the entire economy, and we have an increase of 12,000 jobs in 2030 here, and 120 almost in 2050. Then in the renewable plus subsidies scenario, the situation is actually worse than in the renewable scenario. We have an increase during the period of removal, the first period here, with plus 14,000 jobs in 2025 linked to the recycling of the money within the economy. Especially, I recall you that it was following an employment rule, but then we have a deterioration of employment once these transfers stop. With we observe a decrease of jobs that amount 12,000 in 2030. Then we have a catch-up and significant increase to reach the renewable level at the end of the period. And when we consider the policy package, the low carbon strategy scenario, we have net job creation over the entire period with plus 51,000 jobs in 2030 and 194,000 jobs at the end of the period. Moving to another indicator, which is investment, we observe that the relative trends between scenarios are exactly the same as for employment, with an amplified effect in the package scenario, the low carbon scenario. Let me develop a little bit. In 2050, the increase in investment is similar in the renewable scenario and in the renewable plus subsidies, around plus 7.5%. and plus 12% in the package scenario. This actually can be explained by many things, and very quickly, one point is the significant increase in investment in the electricity sector that is linked to renewable infrastructures and in the modernization of the network. Secondly, the redistribution of the carbon tax revenues and subsidies that encourage investment in particular in depollution processes. And let me highlight the fact that between 2024 and 2031, we have the recessionary effect that prevails in the renewable plus subsidy scenario, since the amount of redistributed are not very high and the share of renewable at that time is still low. Finally, we look at the GDP, and what we observe is that the three scenarios observe a clear improvement throughout the period, reaching at the end a 5% increase of GDP with respect to the reference scenario. Focusing on the short term, the two scenarios with the price instrument are significantly better than the renewable scenario alone. 1% from 2025 for the two renewable plus subsidies and low carbon scenarios, while the GDP variations peak at only 0.23 in the renewable scenarios. Then, from 2030, the renewable plus subsidy scenario shows a worse situation than the other two scenarios. We have economic agents that are less rich in terms of purchasing power, and investment compared to the scenario where the subsidy is maintained, the scenario, the first one, the renewable scenario, as well as the scenario where there is a carbon tax over all the period, which generates income recycled in a virtuous ways in the economy. Before concluding, I wanted to show you at least one result in order to, one sectoral result in order to illustrate the heterogeneity of this result, because until now,
two more minutes.
Okay, it's perfect. Yeah, the idea here is just to illustrate the heterogeneity of the sectoral result. There are some winners and there are some losers. And then in an aggregated way, while recycling the revenues of the carbon tax and the fossil fuel subsidies revenues, it's virtuous. But if we open the box of sectors, the picture is quite heterogeneous. Actually, in this version of 3Me, we have 26 sectors, but here I have aggregated in order to show the sectoral results with it's in French, but industry and agriculture, transportation, services, fossil fuel energy, and other energies, then electricity. And here is the total. We actually estimate annual aggregate employment growth of 95,000 on average over the period. And this increase corresponds to a decrease in the unemployment rate of 1.3 percentage points on average over the study period. But job creation in sectors favored by energy transition policies far exceed job losses in the other sectors. The main sectors that are favored are the industrial sectors and those related to the production of electricity, as we can see here, from renewable sources. And on the contrary, sectors, where is my mouse? Sectors related to fossil fuel activities are experiencing job losses. So this is my concluding slide. To sum up, let's say that the fight against climate change, in particular the implementation of national low carbon strategy in Tunisia, could actually lead to what we call I'm not really comfortable with this concept, but with what we call a double dividend, with a significant reduction in greenhouse gas emission on the one hand, and on the other hand, an improvement of the macroeconomic situation. There is an increase in investment and job creation in low carbon industries that is greater than the destruction of jobs in the fossil fuel sectors, and a decrease in the trade balance deficit, although I didn't show this result. And this national low carbon strategy may induce again equivalent to the income of 2 years of additional growth over the period, which means here particularly 5 percentage points of GDP, with employment increasing by 5% at the end of the period in 2050.
Sorry, time up. Sorry.
Yeah, it's just one sentence. Just to sum up, to say, in order to obtain such favorable economic results, it's very important to recycle the carbon tax revenues into the economy. This is a key element, as it helps the offset of the recessionary effects associated with rising energy prices. So thank you very much for your attention, and welcome. Happy to answer to your question.
Thank you very much, Meriem. A great presentation. I don't know who's first. I see Dominic and then Larry, please.
Thank you, Catherine. Thank you, Meriem, for a very nice presentation. 3 short questions. First, how do you achieve the 80% renewables? I mean, are you, so just, you know, presumably you're not using price instruments, you're using something else. It would be nice to know what you're not able to decarbonize. I suspect it's the transport sector, but you didn't present any results in that in the results. So I was wondering to what extent you're trying to electrify transport, for example. And then with the increase of investment, such high increase in investment, it has to be paid for. So is this coming out of increasing domestic savings or foreign savings? Thank you.
You're welcome. So for the first question, the thing is that here in TRIMI, the electricity mix is exogenous. So the renewables, the percentage of renewables is imposed. It's not reached by prices. This is the first point. The second point about the electrification of the transportation sector, as far as I know, no, there is no electrification. There is, but there is a substitution induced by prices. I still didn't have investigated what's happening, what's going on precisely in the transportation sector, but I think I'll have a look on it. For sure, there's no electrification of the vehicle park. I'm sure of this. So what's happening exactly? Maybe a decrease in the mobility demand, I guess. So I don't know. And the third question was about the increase of investment and why do we have such a virtuous result? That's your question.
Well, since you have to have savings equals investment, if investment's going up, savings has to be going up. So I just want to know what the source of the savings.
I'm not. The thing is that I'm quite new. It's 1 year that I'm in this team modeling, and I'm not very clear with things. But it's not. I have to check. But the savings are. No, I'm going to say something stupid. So. I'll answer you later. I know that there is a question of multiplicator, this new Keynesian model, but I don't know.
May I?
Yes, Juha?
I think you said that the trade balance is improving.
The trade balance is?
It's improving, did you?
Yeah, but that normally reduces foreign savings.
Yeah, that's true. That's true.
I didn't hear what you say. What about the trade balance? I'm sorry.
He said it was improving, but that normally means that the capital account is going in the reverse direction.
Yes.
Yeah, it's true. It should be.
I suspect there's some recycling going on there. So some of the carbon revenues is being recycled into investment. That would be my guess, but
this is, I'm tired. This is for sure, because we don't have these virtuous effects. This is for sure, because when you have no recycling of the carbon tax, we have a decrease in investment. We have a recessionary effect, a decrease of investment for sure. So this is, but the link between here in the model between savings and investment, I'm not very, I have to check. I'm sorry.
No worries. So I move to Larry for the next question. Thank you.
Hello, thanks for another interesting presentation. Actually, my first question is exactly the same as Dominic's first question, but I didn't get you follow your answer. So can you repeat the why how is the renewable penetration target achieved? So the 80%, right? How
it's exogenous.
Exogenous. So there is no cost at all.
No. It's exogenous, but there is no cost at all. There is.
So what is the cost?
The way we do that is, we have a CES function for aggregating all the different power sectors, and we just exogenously change the share parameter for renewables. So you're probably doing something very similar.
Yeah, for sure. But so
it's a non-price change in preferences, basically, for power generation.
So it come from this exogenous, come from this preference change.
Yeah. Well, at least that's the way we do it.
Yes.
They would have something similar. I would think.
Sure, definitely.
Right, yeah. Okay, if that's the case, I can understand why you have this double dividend results, which is was surprising to you, surprising to me, because in general in the literature, people need to face kind of the trade-off between this mitigation policy and the negative impact on the macroeconomy overall. Yeah.
But we don't have this this double dividend when we don't recycle the revenues.
In the scenario of this
only renewables. Yes. Yeah. Wait.
Yeah, GDP investment, employment, all goes up. Yeah. This is anyway, there is another question. So this is I don't know the model at all. So
you don't know what? Sorry.
I don't know the model detail. Yeah. So I assume this is a model for the what is the country name for Tunisia.
Tunisia. Yeah, sorry. But there is sorry to interrupt you. There is also originally it's a model that have been developed for France, and there is a Mexican version from and there is this Tunisian version, and there is an Indonesian version, and the Dutch version too.
Okay. Then my question is that how do you deal with this international trade? Is it just a completely closed economy, or do you allow this international trade in the model? If there is the international trade, then my question is that how do you deal with trade if you impose carbon tax domestically?
Yeah, the carbon tax is imposed domestically, and we assume that there is no climate policy that is done outside the country.
Are you also imposing the carbon taxes on imports of fossil fuels? Because my understanding is that from the background Tunisia economy highly depend on this fossil imports, right?
Yeah, sure. Sure. So the carbon tax is imposed on all the products that are consuming fossil fuel energy. So even if it's most of the fossil fuel energy comes from importations.
Okay.
It is taxed.
Okay. Thank you. Yeah.
Thank you. Then we go to Julio, I think. Yes.
Thank you. Can you hear me?
Yes.
All right. Thanks for your presentation. I have a question regarding your employment results. So these results actually remind me of a paper by Shapiro and Metcalf, who modeled the introduction of a carbon tax in the US, and actually they've also find positive employment effects. However, in their model, they allow for firm creation. So my question is, how do labor markets adjust in your model? And based on that, how can you, if you can provide some intuitive explanation behind your results?
Yeah, behind my results here are triggered also again by the recycling of since one of the rules of the recycling are directly related to the weight of employment of some sectors. You have this virtuous effect. The more your share, the biggest your share of employment in the total employment, the more you receive money, and so then you will have this will generate a virtuous circle of employment. And the other point is about the way the employment market is modeled, and it's a Philip curve. And no, I actually don't know in detail how it works. I know when at the opposite, when you have that you have a slow adjustment of the equilibrium. At the opposite, I can explain, because when you have your demand that follow your supply.
2 minutes for the discussion.
Oh. I'll prepare a proper answer and I'll send you, Julio.
Okay, thank you.
Thank you. If I may, I just have just two quick questions. So one is you mentioned about the reinvestment in the economy, obviously to recapture and get the boost. Did you do sensitivity on which sector that reinvestment should be done? And then my next question is just quickly, and sorry if I missed that, what are the next steps on this research? Because it's very interesting, and I wanted to know if you have started the next steps on this research. Thank you.
The first question was about sensitivity analysis of the results.
The sensitivity on which sector should the gains be redistributed? Or
yeah, no. It would be very interesting, and honestly, I never thought about this kind of sensitivity analysis, but it would be great. We have done some sensitivity analysis regarding the way we recycle the carbon tax, but reducing some taxes, etc., but not considering the targeted sectors, properly speaking. And the last question was, the further steps. The sensitivity analysis. To build the sensitivity analysis, just to highlight the robustness of the results, and to think about doing it quite smartly. And the thing is that this work is also done in collaboration with the Tunisian government, who asked for some quantitative analysis of their low carbon transition. So we are, it's also very dependent on their demand and trying to align our academic objectives and their pragmatic demand, policy demand oriented.
Perfect. Thank you very much. Thank you, Meriem, for a great presentation.
Thank you.
And thank you, everyone, for the great discussion. Okay, so we're moving quickly to our next presenter, Mr. Angelo Gurgel from the Massachusetts Institute of Technology, which will be presenting on quantifying uncertainty in global and sub-global socioeconomic and greenhouse gas emissions futures. When you're ready, please take the floor. Thank you.
Sure. Thank you, Catherine, for the introduction. Thank you, everyone who took the time to attend this session. So our work, it's a collaboration with Stephen Rose from EPRI and Jennifer Morris from the MIT Joint Program. And my agenda here, it's quite common. I talk about the motivation of this work, the methods, scenarios and results, and our conclusions. And going to the motivation, I think several questions can be posed to try to come up with the motivation for this work. So we need to quantify uncertainty about the future pathways that we can follow when we're trying to mitigate climate change. And some simple questions that are behind our main goals has to do with the size of those uncertainties, how broad are the possible alternative outcomes from trying to achieve some stabilization pathway, given all the uncertainties in our socioeconomic structure, how we decide things individually in the microeconomic perspective, and how we collectively in our macroeconomic decisions get at some population growth, GDP growth, or total factor productivity growth in the future, under all those possible ways that our economy will develop in the future, how much different can be that future to achieve the same stabilization target. Another way to pose the motivation, the questions behind our work here, it's related to the way that risk assessment it's being managed, is being addressed today in the current work dealing with climate change or climate policies. How it's a more formal probabilistic approach, how can we address better in a formal probabilistic approach those uncertainties in the future development of the economies. In another way to think about the big picture, the big problem that we have to deal when we talk about uncertainty and risks, it's how much outcomes, costs, and benefits from a given climate stabilization target, that's 1.5C, how they change if we change the policy design or we change the structural behavior behind our economy. And then two more provocative questions that we are trying to answer here. It's how much confidence can we have in a given global regional emissions trajectory, and most of our work is done in that way. We just choose a policy trajectory to reach some kind of emissions level and give a single output of results saying how much energy we will get, how much GDP will be affected, and just looking at one straight scenario, how much confidence we can have in that single result, or a more maybe fundamental and provocative question is how realistic is a world where we go to near zero emissions limits with global carbon pricing, all the countries join together global effort and having a lot of negative carbon emissions in place. So can we believe in that country? How realistic it is? Those are several questions that are in the umbrella of our study here. And if we go to a more formal motivation of our study, we know that we need to understand better all the uncertainty behind the global socioeconomic and greenhouse gas emissions trajectories in the future. And we need that for better climate policy planning and risk management to deal with the impacts, with the vulnerabilities and the strategies that we can come up to fight climate change. We need to understand better those uncertainties to inform about climate goals and the trade-offs in terms of benefits and cost of climate policies. We need to understand those uncertainties if we want to assess some social cost of carbon. And when we are assessing risks, governments and companies can deal with those risks in terms of future pathways of the economy, we need to deal with the uncertainty behind our estimates. So together with this need, our view is that today, what we have done to this point in terms of uncertainty and those future pathways of stabilization, it's quite limited in terms of a more formal way to represent that uncertainty. So there are several pathways, several scenarios, but it's very hard to weight those scenarios or to give some statistical interpretation to those scenarios. When we think about the RCPs, the SSPs, the IPCC synthesis report, assessment reports, it's quite hard to weight which of those futures scenarios are more, what the probability or the willingness to see those things happening. And because of that, most of our work is based on some kind of single global emissions pathway, which doesn't give us the broad possible future societies that we'll get at the same climate stabilization target. So just to give some examples of the importance of trying to deal with this uncertainty or this probabilistic future society, given all the different behavior that we can have in the future. When we think about social cost of carbon, or when we think about IPCC trying to communicate its results, when we try to assess climate risks or design scenarios as SSPs, in all those situations, as example in the IPCC, we have dozens of results, dozens of models. They are doing several scenarios, and even if we try to trim those scenarios to something that's more reasonable, we still get so many scenarios and no way to weight which of those scenarios are the most, have a higher possibility to occur, or under which combination of parameters we would get those more expected development of society in the future under some climate policy target. So how do we try to address this uncertainty probabilistic future that and try to put some more formal representation of probability or structural probability difference in our economies? Well, we just, our approach is just to develop what we call a probabilistic multi-sector coupled human natural system model and explore some parametric uncertainty about climate policy. Then I'm sure how we will do that. And then we can generate a distribution of potential global and sub-global outcomes, or we could call societies, with and without climate policy, and try to understand how broad or how large are the potential different ways society will achieve the same climate target. Our experimental design, we use a comfortable general equilibrium model coupled with a climate model to get at our outcomes. And we built, spend several years building some parametrical distributions of the main drivers of our economic and climate model. And then we designed two broad types of scenarios, and we try to work with scenarios in two dimensions. One dimension is the stringency of our global policy target from a stabilization climate where climate will change, average temperature will change a little bit above 2 degrees Celsius, going toward a climate target of 1.5 degrees Celsius. And another dimension of our scenario design is think about uncertainty in the policies that we will see in the future. So are we going to see a kind of global policy with technologies available at low cost, with decarbonization options in the agriculture systems, reforestation potential, and so on? Or are we going to see a future where countries will not collaborate? Each country will have its own carbon market or carbon price. Technologies will be too expensive, negative emissions technologies will be too expensive. What kind of future we will have? So we draw two extreme scenarios, one where we have an optimistic view and where will be global cooperation, technologies will be available, and another one where we will have a more pessimistic pursuit of the climate target. So just to give an idea about those two dimensions of our scenario design, in terms of stringency, our scenario goes from the reference case where we don't have enough efforts to try to stabilize temperature, and 4 other levels of temperature change, average temperature change, or climate stabilization in the world. And here's just some description of the probabilities behind those targets, those climate targets. And in terms of the dimension of our extreme policy designs, in the optimistic case, we have negative emissions technologies available. The cost is low enough to get to those technologies to get adopted. The institutions are there to measure, account, and credit afforestation and reforestation projects. We mitigate emissions from deforestation, and we have international trading on permits, so a global carbon market and a cap and trade market at a global level with countries trading permits and one single carbon price. And under the pessimistic assumption, we have countries dealing with their own cap and trade markets to reach their goals, but there's no international trading permits. The technologies to capture and sequester carbon are not available, and countries don't need to stop deforestation to achieve the climate goal. So under those combinations of stringency targets and optimistic and pessimistic design, we will test our approach under uncertainty design. Well, usually what we do with our tools is to choose a policy scenario, run through an economic model, in this case, the economic project and policy analysis model. Then we generate anthropogenic emissions of greenhouse gases and other pollutants. We pass those information to a climate model, and the climate model and the economic model together give a lot of outputs, right? So what we are proposing here is to extend this approach to work with probability distribution of the key behavior parameters of the economic model and the climate model. And we spend many time trying to build those probability distribution for those parameters. And I will show some of them in the next few slides. And from those distributions, we sample 400 sets of parameters, and we run our model 400 times for each single scenario to try to understand how broad can be the outcomes under this uncertainty behind the set of parameters we are choosing. So our economic model, it's the Epa model. It's a comparable general equilibrium model with 18 regions of the economy. It has endogenous land use change. It represents several technologies in the energy and electricity sector, including carbon capture and sequestration, biomass with carbon capture and sequestration, and carbon capture and sequestration in fossil fuels. A lot of options for the household transportation sector, bioenergy, and so on. These are some of the input parameters that we build our uncertainty approach, the structural probability approach here. So population growth, total factor productivity, costs of technologies, elasticity of substitutions, trends in energy efficiency, rate of technological penetration, and so on. And I have two of those parameters here and the range of our distribution for those parameters. GDP growth, which will drive total factor productivity in the policy case, and global population. And then let's get at some results when we run our model 400 times for each scenario, right? So those are the scenarios that we are dealing with. Our reference scenario, emissions under the 400 times that we run the model can get at this broad range, depending on the set of parameters, the kind of society that we draw from our distribution of parameters. And then our different climate stabilization targets, they are represented by global CO2 emissions that countries need to achieve together to get at some level of temperature. And it shows the range of temperatures that we get when we combine the economic and the climate model. Again, we have two sets of policies to achieve those stabilization scenarios, an optimistic set of policies where we have negative technologies or actions available. We mitigate emissions from land use and land use change, and we have international permit trading. In the pessimistic scenarios, the world where countries do not collaborate, not cooperate, and there's no chance to do afforestation to get credits or to reduce emissions, or using bioenergy with carbon capture and sequestration. So what happens under those different sets of scenarios? This is our first result. The CO2 emissions under the optimistic policy assumptions for some single country like the US can vary from 2 to 5 gigatons of CO2 equivalent by 2050. So US could be contributing with only 2 tons of CO2 equivalent emissions, or with 5 to reach the same global target. So it gives the range of the uncertainty behind our future society to achieve the 2C target. But if we have the pessimistic policy assumptions, there's no flexibility for the US to help the global target. It needs to achieve exactly the target that we impose to the model, that in this case is 0.5 gigatons of CO2 equivalent. But it doesn't mean that there's no uncertainty behind other results. So if we break out the total CO2 emissions in fossil fuel CO2 emissions and other greenhouse gas emissions, we see that there is a room for trading permits between those two type of gases. And then US could be, under this pessimistic world, emitting more fossil CO2 emissions and less non-CO2 emissions, or could be the opposite, depending on the conditions, the structural conditions of the economy in terms of population growth, GDP growth, elasticities, efficiency in energy, and so on. What does it mean for the energy consumption in the US? We are talking about a range between 40 to 175 exajoules of total primary energy. And we can see if we are under the pessimistic policy assumption, we have much less energy being consumed. Under the optimistic assumption, there's a lot of flexibility on the policy design, net negative technologies out there, trade.
2 more minutes.
Okay. So it will give us a much broader range of uncertainty about the future production of and consumption of primary energy. So we have results for each of the scenarios. This is the close to 1.5 degree stabilization. And then I think it would be nice to show the 1.5 degree. And the first thing that comes to our attention, this graph, is that when we try to run the pessimistic assumptions to achieve the 1.5 C, the model doesn't find solution for most of the 400 runs that we did. It means that our model doesn't find a way to accommodate the 1.5 C scenario stabilization target with policies that are too pessimistic. So no BECCS, no afforestation, and no international trade. The model doesn't find a way to get there. And if we put all the scenarios together, we can see here how the distribution from the reference to 1.5 C shift towards the left in terms of energy under the optimistic and pessimistic design policy, and how narrow or broad are those distributions given the pessimistic or the optimistic design. In terms of costs, it's my last slide of results. We can see that costs can vary from, in the 2C case, from 15% decrease in GDP to 1% increase if we move from the pessimistic to the optimistic assumption. So there is a combination of GDP growth, technology costs that will be very costly to achieve the stabilization target. And as we couldn't find a solution for the pessimistic case in the under 1.5 C, we could assume in our model setup that's the infinite cost to achieve there under a pessimistic set of policies. So I'm not going to discuss those things. Just to wrap up my results here, there is a very large range of outcomes. Society can be very different to achieve the same target, and we need to take into account in our decisions at the state level, at the government level, or at the private sector. We believe that our approach can help to rule out or weight some of the development pathways that we see out there that doesn't have any probabilistic assumption behind those. Well, thank you very much. I'm sorry if I exceed the time. And of course, we have caveats, but I'm happy to address any questions or comments from you guys.
Thank you very much, Angelo. Very good presentation as well. So yes, if we have any comments or suggestions, please raise your hand. Yes, Dominic.
Sorry, I'm always the first, but Angelo, really nice work that you're doing there at MIT with Steve. Just a question on the Latin hypercube sampling. I mean, how many parameters are we talking about, and is 400 draws enough?
Well, it's a very good question. Actually, we are talking about a range of, I believe, 10 or 12 different parameters. But of course, when we think about different countries, it explodes to a large set of parameters. And we have tested the approach with 1,000 samples, and we didn't find reasonable change on that. And we have 2 papers that came out last year that are dealing with this. Okay, it's 400 enough to get a good sense. And the answer when we draw 1,000, comparing the 400 samples with 1,000 samples, is that we get the same very close results in terms of average, mean, and the tails of the distribution. So from the computational efficiency, we believe that 400 is enough to move.
Thank you. Then I think it's Larry.
Thank you for another interesting presentation of obviously this very important topic. So if I understand it correctly, so the approach is to implement impose Monte Carlo simulation on top of the MITC EPA model. And my question is that how do you set distribution for this for your parameters? Because I ask you one reason is that because some people argue that climate change is an unprecedented event. So basically, it's impossible or difficult to know the distribution for some parameter, particularly related to climate change. So I wonder.
I think these are very good questions, and actually the same answer that I gave to Dominic. We have 2 papers that came out last year where we are trying to address those things: how to build the distribution for those parameters, right? And it's where we spend most of the time in this research, and it's an ongoing effort that dates maybe back to 2001 or 2002, right? And there's different approaches, different ways for the different parameters that we use. So as example, when we think about elasticities, we have distribution for elasticities of substitution between capital and labor, and how we get that, how we were able to come up with a distribution function for those elasticities. So where there are some econometric work of those elasticities, usually they report the standard deviation for those estimates. So based on that standard deviation, we create the distributions that we want for those parameters. When we think about GDP growth, there is a lot of studies out there talk about what's the expected GDP growth in the future, or what's the total factor productivity behind those GDP growth. And we try to build one reasonable statistical approach where we will build the distribution for those. So we recognize that we lack enough information to think about future climate change, and we try to address that, trying to reduce our lack of information in the basic parameters that will drive those models. But we have if you want, I can send you the documentation where we explain how we draw the distribution for each of those parameters that we are assuming as uncertain in our model.
Yeah, thank you. I will be very interested. I understand this, but that's probably the best you can do, given this, given there are a lot of uncertainty. Yeah, thank you.
You're welcome.
Thank you. Then we Julio. Thank you.
All right, thank you for your presentation. I have 2 short questions, probably. The first thing that comes to my mind when I hear about your model is how computationally demanding is this kind of model? How much time does it take you to run this whole thing? And the second question I have is if the model is available. It's an open source model. Can we use it? Can we use it? So thank you.
Well, thank you, Julio. They are very good questions also. Well, it's very time intensive. Usually, if everything goes right, we can run one scenario 400 times from one day to the next day, sometimes 24 hours, sometimes 18 hours to get all to have all the results. But just for the economic model, then we have the climate model that can take another day, right? And usually when we run something, we realize that we made some mistake or we didn't pay attention to something. So practically we take maybe several months. I think those results that I showed to you, we are running since summer last year. Before summer last year, we start running this project. And then several times we went back and said, okay, our emission pathways for some countries is crazy, it's not doing well. So we didn't get the right parameter that we should from our parameter distribution. So as it's very computational intensive in terms of machine hours, it's much more intensive in terms of the labor to assemble those things and to revise the materials and see if they are working well. Regarding if it's available, well, we have a version of the Epa model that's free. It's open in our website. It's not the version that we are using here. It's the version that we are using here. It's a kind of updated compared to what we have in our website. And we don't have a free distribution of this setup of combining the economic model and the climate model. But the economic model,
2 more minutes.
The economic model has an open version, and we are planning to release the most up-to-date version of the model at the end of this year or the beginning of next year.
Thank you. I then move to Juha, please, for the next question.
Thank you. Really nice presentation. One thing comes to my mind. Implicitly or explicitly, you are assuming that everybody's sort of rowing the same boat. Everybody is striving to this global target. But there's if you think about integrating climate, then adaptation becomes almost as important as mitigation, and that leads me to sort of wonder what sort of an impact do you reckon adaptation might have to the reaction of the countries? And this is something that we are working on at the moment. And obviously, small countries like the Nordic countries have to take whatever comes with the climate as a given. So there's not really a feedback from our policies to climate change per se. But the expected climate change is having an impact on the policies that we implement.
Yeah, well, I totally agree with you. And this work, we are not dealing directly with adaptation, so we don't have feedbacks from the climate system to the economic system, right? But it's easy to understand that most of our economic models have a lot of ways of adaptation embedded in our elasticities and the way that we model things, right? But I agree with you, and I think maybe one relevant message from this work that goes towards your concern, it's that under 1.5 degrees Celsius, if the world doesn't cooperate, if we don't have technologies as we expect, we will not reach that, or will be much harder to achieve. So what are the adaptation opportunities that we have there that we should rely on if we cannot agree as a global community to go toward those targets? If we don't find policies that are more effective to fight climate change. And the model shows that the adaptation embedded in the model is not enough to get a 1.5 under this setup.
Yeah, it's something about either standing together or falling separately.
Yeah, okay.
Thanks.
Sorry, but it's the time up for the discussion.
Can we just have maybe just 2 more questions?
Very quick.
Yes, Meriem, please.
Yeah, just a follow-up of the computing time, etc. The language of Epa, the programming language.
Is GAMS.
Okay. Thank you. So it was very short.
Dominic, for the last questions, please.
Yeah, it's also a short one. Have you guys ever thought about using one of the simple climate models? It would simplify your setup quite a bit, and it has very low cost for the CG model. So I've been implementing the FAIR model, for example, and it just solves very quickly, obviously.
Dominic, well, I think we are aware, but as we have our in-house climate model and one guy who just running that model all the time, I think we never thought about trying that shortcut, right? And I think the beauty of the program is try to put as much as we can of our resources on that. But for sure, if we were working just the economic team, probably will be much faster and easier if we do that.
Yeah. All right. Good.
Yeah. Thank you very much for the question.
Thank you, Angelo, for a great presentation, and thank you, everyone, for the discussion. So that wraps up our final presentation and discussion period for this session on dynamic modeling of climate change policies. Please help me thank you, our presenters, so Laerke, Juha, Meriem, and Angelo, for the valuable presentation. We appreciate everyone joining us today, and I hope you enjoy the rest of the conference. Thank you.